Hello everyone, it's me Abhishek Thapar. Today I am going to explain about my task number 2 is a data science intern on core class, that is credit card fraud detection. The dataset I have used in this project is taken from the URL of Kaggle website. You can check it out. This project mainly focuses on handling the imbalanced datasets and detecting credit card frauds using following machine learning algorithms like logistic regression, RandomForest classifier, and so on. These models are fitted to different datasets acquired after the standard scalar, oversampling, undersampling, and smooth techniques. Thus, separate files are created for each machine learning model so that every dataset acquired after above mentioned techniques are fitted separately to our model using single function. Look, this main is our main file where we have done the pre-processing, loading of datasets, pre-processing, and exploratory data analysis and visualization. And I have created the separate files for each machine learning models like random forest classifier. Look, this is Bayesian decision tree in this way. Now let's move forward. These datasets have 492 frauds out of 284,807 transactions. So it is a highly unbalanced or imbalanced dataset. It contains only numeric input variables which are the result of a PCA transformation. Due to confidentiality issues, the original features are not provided and more background information about the data. So features V1, V2, V2 to V8, V28 are the principal components obtained with PCA. The only features which have not been transformed with PCA are time and amount. Feature time contains the second elapsed between the each transaction and the first transaction in the dataset, but we did not consider the time for training purpose as it is of no use to build the models and may not impact our target variables. This is our assumptions. I assumed. And the feature amount is the transaction amount. This feature can be used for the example dependent cost sensitive learning. And the feature class is the response variable and it takes value 1 in case of fraud and 0 otherwise, and this is our target variables. Now I have gone through the following steps in order to accomplish this project. Now let's just have a cup of coffee in front of you and explore. Let's dive into the project. Step number 1: importing libraries and loading datasets. I have imported the libraries like pandas, numpy, matplotlib, c1, and I also used imported, but I don't use this library or module for this project. This is just for the text customization, but I have not used, unfortunately. So moving forward, loading dataset I have loaded. And in step number 2, data preprocessing and preparing datasets, checking for any missing values. There are no any missing values. Also another way of checking, this gives the boolean, it return the boolean values false, that it means there is no any missing values in our dataset. Checking info of our datasets, information about our datasets. Now also observing the statistical distribution of our datasets. Now dropping the time attribute. Previously we have discussed in our about dataset portion that we are not using the time attribute as it is of no use to build the models and may not impact our target variables, so that I drop the time uh, attribute for our training purpose. Now x and y are the dependent and independent features extracted from our normal dataset. Now I have extracted the dependent and independent variables from our normal datasets. Please remind this variable x and y from our normal datasets. I will be using this value in in various modules like random forest, logistic regressions. So please remember this variable. Normalizing amount attribute using attribute values using standard scalar. I have also tried with the min max scalar and got the similar results. So for the demonstration I'm only showing the results or results of different machine learning models on the standard scaled dataset. So you can try and experiment with various scaling techniques yourselves. I have just made a copy of and saved to the temp underscore df, imported the standard scalar from the sklearn.preprocessing, and also remember this variable x underscore scaled and the y underscore scaled are our dependent and independent features extracted from our scaled datasets. I will be using this variable. Now, exploratory data analysis, EDA and visualization, making the data ready for plotting of our count variables, count values of different cases. So I am doing this in order to get this result. And now I'm plotting the bar graph using the C1. So I'm using the SNS dot, and you can check it out. And I have plotted this little bit giving little bit of more height is in order to visualize this line for the fraud values, because fraud values is very less 492, and this is too large. So it will not be visible if I will be making I if I had made this height small. So there are 492 fraud tuples, and 2,84,315 tuples with the normal class attribute. Now analyzing before plotting the graph of variation of amount per class. Now I will be plotting another graph. So for that I'm doing analysis. So you can see that fraud data sets are 492 tuples, and 2,84,315 are of normal tuples. And you can see the percentage of fraud transaction in our data set is 0.17 percentage. And the minimum value of amount attribute is 0, and maximum is 2,125, and mean is 120. So there is huge deviation in our amount attribute. So I have already scaled it using the standard scalar. So I did normalization before. So I'm just plotting these data sets values, actual data set values in the histogram. So this is our histogram. Look, all the fraud class attributes, all the tuples having the fraud as a class attribute will have the values, are having the values uh, of amount less than 2500, and they are in less amount. There are very less number of transactions having these values, and all values are look 2000 2500, below they are 2500. But our also our normal data sets consist of great large number of values below 2500. So it is really tough to differentiate. But also all those values with amount greater than 25,000 $2500 dollar are can be considered as a normal. So now moving forward to step number 4, handling imbalanced data sets. Techniques to handle imbalanced data for a classification problem. I have gone through this blog of analyticsvidya.com, so you can check it out. I have given the references. First, uh, in order to handle the imbalanced datasets, we need to choose the proper evaluation matrix. Accuracy may be good enough for a well balanced class, but not ideal for the imbalanced class problem. So other metrics like precision measure of how accurate the classifier's prediction of a specific class, and the recall measure of the classifier's ability to identify a class are also considered. For an imbalanced dataset, F1 score is a more appropriate metric, which is defined as the harmonic mean between the precision and the recall. F1 score ranges from 0 and 1, and the closer it is to 1, the better the model. Now, resampling, another step, another way to handle the imbalanced datasets is resampling. And there are two ways in resampling. One is oversampling and another is undersampling. Oversampling, In oversampling, our majority class is with having large number of tuples. So 0 class has 284,315 datasets, and our class with that is minority class with class value 1 has only 492 values tuples. So in order to um, upsample our minority class to the value is that of 2800 284,315, we are changing our minorities. So class 0 is a d of majority saving, and class 1 is a d of minority, and we are oversampling the minority class. So resample, and we are over resampling the d of minority. Replace equal to true means there may be the repeat duplication of tuples. So and n samples is equal to, we are making resampling to the sample values of 284,315, which is equal to the majority class. And the random state 42 is just for making consistent resampling. And df undersampled and we can concatenate finally, and df oversampled class values. If we see the result, both the class now are balanced. Thus our dataset is balanced. And just remember this these variables, x underscore oversampled and the y underscore oversampled, our final sample datasets, and I will be using this variable. Now again, the undersampled, for undersample I am using the random undersampler from the imbalanced.undersampling module. And after undersampling, I will be getting both the values of the majority and the minority class with the tuples 492 and tuple values of 492 and 492. So our this much 284,315 tuples are reduced to 492, which is equal to the number of the minority class. So this is undersampling. And another way is the smooth, that is synthetic minority oversampling technique. Simply adding duplicate records of minority class often don't add any new information to the model. In smooth, new instances are synthesized from the existing data. If we explain it in simple words, smooth looks into minority class instances and make k-nearest neighbors to select a random nearest neighbor, and a synthetic instance is created randomly in feature space. Now for that I'm importing smooth from imbalanced.oversampling. And this way, now remember this these two variables, x underscore smooth and y underscore smooth, which will be which I will be using for model fitting. And now with this I am now going to the logistic regression module. Look, now what I basically doing is that from the main attribute, I'm just doing the pre-processing, loading of datasets, and explorative data analysis and visualization, and making the datasets ready for model fitting. So I am importing the main.ipynb in order to use the prepare datasets of main.ipynb. So I will not be repeatedly doing similar data preparing processes just as I did in main.ipynb file. So just for reducing for making the dry codes, our code dry, I am importing the main.ipynb. And for this I have used this code. You can go from the this following code in order to import. Now importing necessary libraries, again I am importing the necessary libraries. So I am using the logistic regression. So I will be using the I will be importing the scale underscore model from, and importing the logistic regression. Now I am making the function. Look, this is my function, which will which will first split our data sets. That is, it will take the x and the y independent variables and split into the x train, y x traced, y train, y test using the trend test split. And then it will instantiate logistic regression. Then after that it will compute the class. It will also prepare the classification report and print it, and make the confusion matrix on the trained dataset firstly. Then it will be plotting the confusion matrix on trained dataset. After that it will be doing the prediction, it will be doing the evaluation on the test prediction. And it look on x underscore test, I will be doing the test prediction on x underscore test, and the plotting the and printing the confusion report, and printing sorry and computing the confusion matrix of y test, that is on testing data sets. And I will be plotting the similar type of confusion matrix and printing out the accuracy score on the training and the test data sets both. This function is doing this. Now you will be clear, much more clear from the output. Now first I am doing the logistic regression on normal data sets. What I am doing is that I am calling the lr underscore model, this function, and passing the values main.x comma main.y. This why I am doing the main, because I am importing the main.ipynb, and this x and this y are the variables of that main.ipynb. This is so you can see that I will be showing you so that you will be more clear. Look what I said, please remember this variable, and I am using this x and y in order to train our logistic regression. So I am using the main.x and the main.y. So this x and the y will be passed into the this function and as x and y, and this x and y will be splitted by the train test split, and further evaluation will be doing like model fitting, classification report, confusion matrix, accuracy score, like this. And our dataset is splitted successfully, model fitting begins, and there is some error. So please ignore this error for a while, because this is just a warning, not error, sorry. And our accuracy score look 99.925 on testing training predictions, and test predictions is this much. But you can see that our we are focusing more on the f1 score, and this macro average is the one which we are focusing, because macro average is of f1 score. This is the average of both these both classes, both f1 scores of both 0 and 1 class. So this is 0.84 is the average of 1.00 and 0.69. So we'll be more focusing on this value, and we are trying to improve accuracy as well as macro average of f1 score. Look confusion matrix, but there are lots of error in training, because this is the confusion matrix of training. This is first one is the for the training predictions, and this is for the testing predictions. So there are lots of error, and you can see that the logistic regression on standard scalar datasets. So I have used the main.x scale and main.y scale. I have passed this parameter. What is x underscore scale? Please go look x underscore scale. Look this value. I'm just passing the standard scaled value. So in order to for the model fitting. So this is the logistic regression on standard scale datasets, and our result is like this. You can go through this. Lots of error, because logistic regressions do not work efficiently for imbalanced datasets like this. And I'm doing the undersampled sampling techniques. So for undersampled datasets, I'm passing the parameter like x underscore undersampled main dot y underscore undersampled. And you can also see what is this variable. This is the variable I'm using. You can see that this variable x underscore oversampled, x y underscore oversampled, and I have fitted like this. And again on oversampled datasets I'm also doing the same. So this is why I'm making the function at the beginning, because I'm using that code repeatedly. So I have made a function and passing the parameters, independent and independent parameters, and calling the function repeatedly in order to do our model fitting evaluation as well as a visualization. So you can go through this, the result. And also on the smooth datasets, main.x smooth and main.y smooth passing is the dependent and independent features. Look, what is x smooth and y smooth? Look, this is the variable I'm using of the main.ipynb file. So now moving forward, now from conclusion, logistic regression does not work efficiently for this imbalanced dataset, because there are lots of true negative, sorry, false positive and false negative values, and it takes around 1 to 2 minutes for training purpose, which is really faster method or faster technique. And the maximum accuracy of maximum accuracy of 99.91222% and macro average of F1 score of 0.85 achieved with standard scale dataset. This accuracy is also of great value. So but after observing other model accuracy, you can see that why it does not work efficiently for this imbalanced data sets. This accuracy will be considered as little low, because f1 macro value is 0.85 only, using the standard scale data sets for the logistic regression. Now let's dive into the random forest. In order to use the prepared datasets of main.ipynb for model fitting, we need to import the main.ipynb. So similar approach, just like the logistic regression, I've imported our main.ipynb in order to use the attribute value variables like x underscore smooth, y underscore smooth for model fitting. Now this is random forest. Now I have made the rf underscore model for random forest, and similar approach like that above I have done, and model fitted main.x main.y, and you can see the output. I'm just scrolling down because these are all the steps which I already explained for the logistic regression. Similar approaches, just look how much well the model fitted for the training datasets. Also this result shows the quite great efficient accuracy score than that of the logistic regression, with the macro average value, better macro average value of 0.93 for the standard scale datasets. Now similarly, for the undersample datasets, it is working little bit fine, but not as much as previous on previous datasets, is like previous datasets. So now just scrolling as soon as possible. And for with the oversample datasets, look, the model is fitted very well with the 99.9964% of accuracy, which is really quite high, with the macro average of 1, which is the maximum value of the macro average. So this could be considered as one of the finest model with oversampled datasets. Now on smooth, also it is giving quite really high efficiency, but from the conclusion we can say that the maximum accuracy of 99.9964 and macro average of F1 score achieved with oversampling technique. And undersampling does not work efficiently for the large majority class datasets, as it ignore many valuable tuples. So for the large datasets, we need to in undersampling process, we need to ignore many tuples, so that it will be reduced to the equal number of tuples is that of the minority class. So but can be efficient for small majority class datasets. Also random forest works efficiently for this imbalanced datasets. Random forest takes 10 to 15 minutes for training, so it takes huge amount of time for the training purpose. Now let's dive into the k-nearest neighbor. Similar approach I have gone through the similar approach. I'm just scrolling down for this model fitting k-nearest on normal datasets, giving really quite good efficiency, better efficiency with the k-nearest neighbor. Also k-nearest neighbors on the standard scale datasets, k-nearest neighbors on the undersample datasets, poor accuracy for undersample datasets. You can see k-nearest on oversample datasets, k-nearest on smooth datasets. Now k-nearest works even efficiently for these imbalanced datasets. It takes around 3 to 5 minutes for the training, and the maximum accuracy of 99.967% with the macro average of 1.00 achieved with oversampling techniques. Now let's dive into the Bayesian. Similar approach. So I'm just scrolling, creating the GNB, that is GaussianNB model function, and calling the function repeatedly for various independent dependent variables. Bayesian is not performing uh, as much as I expected. It is giving very poor accuracy. This is not poor, but as compared to the other model which is giving the 99% accuracy, it is very less than that of the previous models. So GaussianNB, that is Gaussian does not work efficiently for this imbalanced datasets. It takes around 1 minute for training. That is faster, very faster, and maximum accuracy of 91.8866% with macro average of 0.9 to achieve with oversampling techniques. Considering both accuracy and the macro values, we need to consider both the macro values and the accuracy values for the for considering the uh, efficient model for the imbalanced datasets. Now without wasting much more time, I'm going to the decision tree. Let's go through the decision tree. I'm creating the function decision tree, that is dt underscore model xy decision tree on normal datasets, dt underscore model. Then after that I'm going through a decision tree on the standard scale. Similar approach, so I'm not going repeatedly through the detailed explanation. Just you can understand from the previous model explanation how it working. All are similar, working is similar through the similar approach. So just go through one approach and you can get the idea about all the other models easily. So I've constructed very easily all the files with the similar approach. Now you can see I'm just going through the conclusion. Look, also decision tree is not working quite as expected. 28, okay, nice. Now decision tree works if even efficiently for this imbalanced dataset. It takes around 1 to 2 minutes for the training, and the maximum accuracy of 99.97 with the macro average of f1 score 1.00 achieved with oversampling techniques. Now let's see oversampling. Oh, in our conclusion. And now the XGBoost. Let's talk about this. I have installed the XGBoost and XGBCLassifier from the XGBoost, and similar approach definition, function definition, passing the XY, instantiating the XGB classifier, and feeding the model to the data, and doing the prediction on the trained datasets, confusion matrix, printing the classification report, accuracy, and again on the test prediction, test similar approach. Now XGB classifier on normal datasets. Oh, well fitted on training datasets. Now this is for the test datasets. Really good, very high accuracy with the macro score of macro average of 0.94. Nice. And just giving the 2 and 19. Okay, very good. XGB classifier on the standard scale datasets. And for the standard scale datasets, it is giving quite similar results as above. On undersampled datasets, less accuracy than above. On oversampled datasets, look, I'm passing main.x underscore oversampled, main.y underscore oversampled. This variable you are getting from where I am using this variable. So I'm not explaining here. If you are jumping directly to here, please get back to the watch this video from the beginning, so that you will get how this variable comes, why I am using the main dot here. So don't skip especially at the beginning. After logistic regression, you can skip videos and just see the code, so that you can also get easily understood. And accuracy of 99.93845%. Now very good. And 7 are only errors. Now with the smooth, we can see 25.0. With the smooth, our model is the data, our model are not predicting as much as better than that of our oversampling techniques. So again, the undersampling does not work efficiently for the large majority class datasets, as it ignores many valuable tuples, but can be efficient for the small majority class datasets. It works even efficiently for this imbalanced datasets. Yes, we can see. And it takes about around 1 minute for the training. So XGBoost with better accuracy, also with better or faster training speed or processing speed, and maximum accuracy of 99.9938% with the macro average of F1 score 1.00 achieved with oversampling technique. Now let's move at the conclusion part, that is the step 5 of our main.ipynb. Out of 6 machine learning models use, RandomForestClassifier works efficiently with maximum accuracy of 99.996483% and the macro average of 1.00 achieved with oversampling technique. So oversampling techniques prove to be efficient for handling imbalanced datasets. RandomForest, XGBoost, DecisionTree, KNeighbors works efficiently even for this imbalanced datasets. RandomForest takes a lot of training time among all of the 6 models. So I have waited very and spent lots of time for the training of the RandomForest model. So just be patient while doing the model fitting. It might take more than 15 minutes if you're processing if you have lower processing laptops or computer. So just be patient. And now the further enhancements, I have used the default hyperparameters during the model instantiation, so you can play with the hyperparameters for improving the efficiency of our models. You can also apply other machine learning models as well. And finally, I would like to thanks all of you for visiting and exploring my ideas and the course. Glad to share to this, and thanks for the opportunity to code clause to improve and enhance myself in the field of science. And the references, you can visit these references for better understanding. And also you can contact me on LinkedIn, and this is my LinkedIn profile link. You can visit my YouTube channel. This one is my YouTube channel. And the uploaded video link of this task was coming soon. Now I will be uploading this soon and making the changes here. And now I would like to say that please do like and subscribe and support me. Thanks every passionate learner in advance. Also don't forget to reference my contents if you are sharing anywhere. Thank you so much.